So good afternoon, everyone. Today we are having a very special guest, Professor Michał Ostrowski from Krakow, from Astronomical Observatory of Jagiellonian University in Krakow. And he will tell us a bit about something that we haven't heard in this semester yet, because of some extremely low frequency electromagnetic waves in the project that is actually developed for 30 years or something like this, and we will hear about the results. So, Michał, the floor is yours, and let me remind also the students, master students and PhD students to put your names there. So, thank you very much.
Okay, thank you very much for inviting me here. I will be very glad to tell you something about my work, which is now very far from what I can still continue in high energy gamma ray astrophysics. Essentially, high energy gamma ray astrophysics, we consider gamma rays in energies of 10 electronvolts or more. These frequencies is 10 to 29 hertz. And now I would like to tell you the other how to say, to completely different range of frequencies, namely to frequencies even below 1 hertz. So something like 30 orders in magnitude in lower frequencies. I would like to speak today about our project, which is continued for a long time in the observatory. And essentially, I am presenter, but there are many people involved in this project. And essentially, in particular, Andrzej Kułak was initiator of these studies some 30 years ago. Probably I have here a picture of our first measurements, which were done in Bieszczady Mountains. Bieszczady, because its environment is very low electromagnetic pollution. So, what is the situation now? We do measurements in the frequency range now with our recent magnetic sensor LI11 from a fraction of hertz up to kilohertz frequency. And there are many people involved in this study, including me and also our colleagues from Jagiellonian University of Science and Technology. And we closely collaborate with Margot Kowski from Denver. And there are some people who contributed significantly to this research earlier. In this moment, our main station is in Bieszczady. Maybe I don't know exactly, but maybe somewhere here. And the station looks like that. So it's not a very modern radio telescope or a dome for a telescope. Simply, our measuring facility is covered underground, especially container underground, which allows to keep temperature above zero full year. And also, it is not possible to carry electric power here with wires because it would disturb our measurements. So we use batteries here in this receiver. And our antennas are somewhere here. Among trees, they are inside deep into the ground, and just protected against any damage or speeding there. It is important that in these low frequencies, waves are transmitted easily deep underground, and because of that, this cover of ground simply helps in observations and not makes any absorption for the lens. Inside our container, it looks like here there are batteries and our electronics part of the system, and some 100 meters from this container there are magnetic antennas. And here is, oh, sorry, here is Europe, which is our main engineer in this project. And also, I would like to show that these are also interested in our status. This picture was taken some tens of meters from our station. In fact, this Pilaty station in Poland is our main station, but we have also two additional stations for nationals, one in USA, close to Denver, operated by Cracow, and another station in Patagonia, in the very southern part of South America, which is operated by people from Buenos Aires. What are our measurements for? We measure low-frequency electromagnetic waves which propagate between the Earth and the ionosphere. This schematic wave is presented here. If we have, for example, a lightning due to thunderstorm in one place on the Earth, low-frequency waves generated during such lightning can propagate several times around the Earth before being absorbed. So because of that, our station may be any place, for example, here in Poland, to do measurements of thunderstorm activity from full Earth, full globe. And so this cavity between ionosphere and Earth, circular cavity, is called Earth ionosphere resonance cavity, and it is this resonance means that some resonance phenomena are occurring. Having many waves generated by many lightnings, one can observe that they interfere with themselves, creating characteristic resonance peaks, so-called Schumann resonances. Here we have in the range from 0 up to 50 hertz. Here is electric power line signal. And we have at 8, 40, 20 hertz, and so on. We have this resonance. Here is also a small line due to railways in vicinity of the station. So, what kind of phenomena we could study in this way? There are plenty of electric phenomena in the atmosphere, and much of them are related to thunderstorms and various discharges, more or less powerful. But there are also some discharges upward toward ionosphere. There are so-called sprites, which are waves in the ionosphere. Here is the high end of the Earth, so it's from 0 up to 100 kilometers presented on this plot. So, okay, so at first, because I'm in the Astronomical Observatory, at first I would like to say a few words about our collaboration with teams carrying gravitational wave detection in Virgo, LIGO, and now camera observatory detector. So it was in 2013 that the people from gravitational wave community realized that this low frequency magnetic waves can disturb their measurements by generating circular currents in the equipment, which result in some forces in the measurements and possibly could generate coherent signals in different detectors. I was presenting that there are very long waves involved in these low frequencies. 8 hertz, it is a wave with wavelengths equal to the equator length, 40,000 kilometers. So, you know, and essentially the frequencies considered are just frequencies which are also considered for in the present day gravitational wave detectors. So, here I can show, for example, measurements from our Pilate and Hugo station in US, and one can note that there are plenty of impulses observed in both stations, which essentially are from a single lightning. So we can expect that the same effect should be should occur in gravitational wave detectors. And if there is any coupling between this magnetic field fluctuation and the measurement in the interferometer, then of course there may be false signals for gravitational waves. So because of that, we started collaboration with the gravitational wave detector groups. And there are a few papers which were written mostly by these people from the detectors, but we contributed there our computers, our expertise in analyzing this low frequency magnetic perturbation and our data from our detectors. And one of areas was by Izabela Kowalska-Leszczyńska, but I can show few results from these 3 papers we published the last year. And of course, because of this collaboration, we are also a part of this whole collaboration. So in this, here are several conclusions written from the paper indicated here, but essentially this paper shows that there may be influence of lightning discharges which are distant from various stations, but which could produce a similar magnetic fluctuation in quite different stations. And here is the Krakow station is here, which is relatively close, but it is more than 1,000 kilometers from Vigo station. And here is Vigo station is more or less in between of 2 LIGO interferometers in US. So in this time also there was discovered that large so-called giant jet from the Thunderstorm to the Jagiellonian, which occurred nearby to Vigo at Sardinia, was also measured by the gravitational wave detector. So it was also proved that such effects can really lead to measurable fluctuations in the detector. So there were several next studies with Michael Collin et al. the interest was mostly related to stochastic gravitational wave vector, which people believe to or intend to measure. And the result of analysis says that in principle, if we take into account information from the magnetic sensor in this extremely low frequency range, then we should be able to allow for detection of such stochastic gravitational wave pattern. One should remember that for such background, people do not measure individual cases of the wave, but more the coherence of signals over 1 year or longer times between different detectors. And I showed you some results which were obtained using also data from our station. And the third last publication where we contributed was Israel, and the conclusion was that now there is no danger of to be influenced current measurements by magnetic field, but future runs could be affected. I will not describe details of this paper because it is not so important. It is important that these factors should be controlled and should be checked against it when considering very long time correlation between different. So maybe I can say a few more words about our recent work. There are several studies which were carried or are under elaboration now, and particularly the propagation of ELF, electromagnetic wave impulses, and testing the ionospheric non-uniformities of such propagation, impact of solar flares, also solar, also space weather on our ionosphere, and various other effects which are also considered and sometimes we can see interesting results. Let me say a few words about the main physical system which can be partly studied using this extremely low frequency wave. Then I don't want to describe in detail of this plot which is borrowed from Wikipedia, but one can see that when we consider ionized media and magnetic fields and ionizing radiations or energetic particles in Earth's vicinity, then they form a very complicated system with some non-uniform ionosphere and some irregular bubbles in the ionosphere and some currents flowing there and energetic particles which reach the Earth and may influence the ionosphere. Not only what we can directly from the sun as ionizing radiation from the sun, UV X-rays, also gamma rays, but the star. So, if you would like to understand better the role of these different factors, probably we should at first look into electromagnetic emissions from the sun, which shapes ionosphere significantly. if we look in a schematic way, the night part of the ionosphere looks like here, that we have increased the densities of ionized particles above 100 kilometers and above or in the range 200 to 300 kilometers. There are layers E and F. During the day, when we have continuous emission of ionizing radiation, a new layer forms. Sorry. D layer forms at lower heights up to about 60 kilometers. And there is also splitting of this F layer into two parts. So if one looks into various emissions, one can see that possibly X-ray emission from the sun can generate this D-layer structure, while the ultraviolet emission mostly it has influence of these higher layers of the ions. And of course, longer emissions can sometimes penetrate quite deep, but they don't ionize, so they don't take ions. But there are various types of phenomena or testing which are used to study ionism. What we can do with our data. Here is an example of our measurements. Here is 5 minutes of measurements with two perpendicular magnetic antennas, east-west and north-south. One can see that there are several impulses due to strong lightnings or nearby lightnings during the day. If we consider a power spectrum of this data, 5 minutes data, one can see it is a logarithmic frequency here. So it is 10 hertz here and 1 hertz here. And so one can see that we can see several Schumann resonance peaks and also 50 hertz electric power line, also some harmony of this electric power line. And apparently, this power line has a lot of power in it, so to make measurements of natural waves generated somewhere around the Earth, and once we move it, if we look into our own data, one can see that here also. So one can see that here we must be in essence, one can see a clear indication of 50 hertz fluctuations. So it is clear that for large impulses we can do measurements even without using raw data. But if you would like to use lower amplitude fluctuations or more distance lightnings, which we are partly attenuated until coming to our here, we have to filters which we have. There are various filters which we can use to filter data. One should note that it is only 1 second of data presented. So we can see so many different so one can see plenty of these individual spikes. I will show also one spike with higher resolution. It is here and it is related to our this plot is related to our published paper about new methods for determining average of ELS signals. So, having our raw data, we can try to direct azimuth of ELF signal, receiving our sensor in very short times. So earlier approaches usually try to model full spike, and it is very sorry. I should note that on this scale there is a sensor image, and roughly 10 sensor units means 1 picotest. Very low magnetic fluctuation. But here we have something like 8,000 sensor units, so 800 picotest, a very strong input. And usually one uses to model full input and tries to derive from both antennas the azimuth of the unit. We decided to use a different approach. When we try to derive azimuth from two successive measurements. From two successive measurements, we can derive changes of magnetic field around the perpendicular axis of our antenna. And from these changes, one can use it for deriving azimuth of the aligning well. Of course, we don't know what is the polarization of the lighting which we study in such a resolution. So in principle, if we have one spike, then we can see that if it is growing, we measure azimuth roughly 80 degrees, but if it is declining, the derived azimuth from this scale is minus 100 degrees. So it is because there's no information in the signal what is the real azimuth, because essentially the same would be opposite azimuth if we have discharge, positive or negative discharge in the lambda sum. So essentially, in principle, we obtain for symmetric impulses, we obtain azimuth from growing and declining part of the discharge 180 degrees. So, and let me stress that here for this type, I show only 6 milliseconds for the consideration. So with our sensor, we do 3 measurements per millisecond. And this approach allows us to consider azimuths from so many points that sometimes there are few discharges on Earth reaching our sensor in the same time, and then the azimuth will be falsified. But there is roughly 50 to 100 electric discharges per second. So it means that roughly 10 milliseconds is between 10 or 20 milliseconds is between 2 successive discharges. So we can expect that at least significant part of our data will carry information about the real azimuth of and to study this method, we use a special day, which was it was 15th January 22, when there was a large volcano eruption in the Pacific Ocean, and I present here a different picture from different eruption, a picture of strong lightning occurring during volcano eruption. So in this case, we have really a point source for strong ELF signal, because here it was measured that some 200,000 lightnings were observed during the eruption. And let me show here the power spectrum or dynamic power spectrum, how changes the power spectrum of our ELF signal during the day is universal time here on 15th January. And each line, each vertical line, is a power spectrum from 75 seconds of measurements. And one can see that here is some maximum, another maximum, and this maximum, it is maximum of the first Schumann resonance peak, second, and so on. These peaks sometimes are stronger, sometimes weaker. But we also see very strong increase of intensity between 4 point something and 6 a.m. And it is exactly when the main volcanic eruption occurred. Also, one can see that secondary eruption, the weaker one, was close to 9 a.m. And one can see a kind of increased emission there. This intensity of emission, this power spectrum. One can note here, and I don't know if you can see here a line, more or less, going. So it is not super resonance, it is 60 hertz emission from 60 hertz systems in America. Also, another interesting feature is here it starts around here, 11 a.m. And the line is at 82 hertz. And now we know that this line is used, these emissions are used to communicate by radio with the submarine. It is important that in this frequency range, these waves can penetrate ocean water, that's up to 300 meters. So possibly they don't send information because frequency is so low, but maybe there are sometimes such things which may be a command just to put a sound on the ocean talk to receive a command through the satellite system. Okay, so then here is harmonic line to this. Okay, so here was one characterization of our measurements. Now we can see how we can use it for derived azimuths. And of course, the azimuth which we could compute depend a lot on what amplitudes are allowed for these changes between successive measures. If we take all the completely black pattern, so here we show that this is 4 plots similar. Here we show our data, our measurements. And on the upper plot is the azimuth from plus to minus 180 degrees. And we know that there should be symmetry, so if there is azimuth of 50, there should be also azimuth at minus 130, for example. And one can see that there are some directions which are rise in observing azimuth. And here we have 300 seconds, and we will take shorter periods. We can use different parameters. Here is already 12 seconds of data, and one can see the numbers of sometimes they stop to be active for maybe 1 or 1.5 seconds. And another part of the data which without any strong spike here where we cannot measure very accurate these different thunderstorms. And this data which I presented earlier, when we have very strong spike, then we can clearly measure azimuth from this and few so what are results? So maybe I could start in this plot. Here we used only very high amplitude spikes for measuring azimuth, and one thing you know is that essentially also here is the time during the day from 0 to 24. This is azimuth from plus 180 to minus 180. And essentially, if there is thunderstorm at a given azimuth, then we can observe it as an increasing density of measurements from a given, showing a given direction. So we can see that we can resolve here maybe 20 thunderstorms on the Earth when observing very high amplitude. But of course, very high amplitude means also that possibly very distant thunderstorms will not be visible here. And one can see a difference if he goes to the lower amplitude to the allowing for lower amplitude changes in magnetic field, because it is for the same day, but here we can clearly see a signal which comes from the Hunga Tonga volcano eruption from the Tonga source. And for example, at 5 or 10, 10 past 5, one can see that this signal is dominating significantly. Here is the number of measurements and azimuth. And this signal here of this signal is dominating significantly all other thunderstorms on Earth. While in the evening of the day, there are plenty of spikes, many thunderstorms in different azimuths. One can go, one can use the lower amplitude, lower amplitude changes, and then resolution is getting poor, but the contribution from this distant and powerful center in the volcano eruption is really quite significant, very well visible, and also very well visible on this. For example, I show also the plot which could be obtained if we test for azimuth determination, if we take the points which are 1 second distant one from the other. So it means only very long waves, such waves can be generated by geomagnetic perturbations, and the wavelengths or time space maybe of the order of tens of seconds even. So here one can see very interesting structures showing that these long waves are generated during the night at some directions, and then changes during the day, and in the evening some systematic variations are also observed. And I cannot explain it exactly now, but it was interesting. such effect. So in this moment, there are three papers submitted from our group, and partly related to this new method of azimuth determination, and partly to more detailed monitoring of lightning impulses, which used to determine the conditions in the ions. So let me mention here, before I go to the first paper, that if we have a range between the day and night, then this transition part on Earth is called terminator, solar terminator. I think people roughly here, maybe they have astronomical light, and people here, where the surface of the Earth is from the surface of the Earth, you can see the sun, and then there is the sunrise for us. But one can see that some particular structure is changing. So we have this ionosphere, and here on the day side of the Earth, there is a lot of ionizing emission from the sun, which changes the structure and increases the density of the ionosphere. So we have here ionization gradient between night and day, and it may be of interest how waves propagate in this. And here are our measurements of azimuths. So it is a day in September, I don't remember exactly, in September 23. And one may note that and these lines are to show that the first yellow line shows when at our Pilates station ionosphere at high of 200 kilometers above Earth is irradiated by the sun. The second one, it shows when it is only 100 kilometers above the Earth. And the third one shows when sunrise is visible on Earth. So one can see that quite interesting structure appears here between this second and third line, and which continues even further on. And we interpret this structure as refraction of the ELF waves propagating due to this gradient of ionization. So essentially, one could say that here thunderstorm, possibly from America, no, America should be here. So maybe from Africa. It's more or less the same as with only some changes due to thunderstorm propagation could influence. Yeah? But then there is a sudden change of direction, and it may be up to 22 degrees. And quite opposite change may be observed during the sunset. So it was very interesting to measure this difference in ELF wave propagation. And additionally, during these measurements, we also discovered we call it gray path for ELF propagation, which is analogy to gray line of high frequency radio propagation. In radio, people sometimes discover that when observing along the terminator, sometimes they can see much stronger signals from distant stations. And in our case, in some days, one can see that before this increase of azimuth during this terminator passage, there is also a negative structure which indicates more efficient propagation. I don't know if it is visible here, but anyway, one has to consider the thunderstorm in Africa, which propagates along the terminator to our station. And apparently there must be opposite gradients of ionization between day and night, at least for part of this length. Please ask questions because maybe I don't know. But here you can see that these structures are not the same every day. There are all certifications September 23. One can see it is only a part of the previous laws from 0 from 1 to 7 AM UT and onwards from -45 to plus 135. One can see that the structures in the successive days are not the same. They change and apparently this indication of non-uniform is ionicity. So we believe this method is very new, very additional and effective tool to study lower ionicity. Here one can see also a nearby thunderstorm. If thunderstorm changes, if thunderstorm changes direction very fast, within 1 or 2 hours, it means that the thunderstorm is passing through the place. So on this plot, this previous slide, we also observed that at one moment after 2 p.m. there was a boosting of our measurements in many different azimuths. So it looked as a failure for the detector, but then we compared to the satellite measurements of the X-ray emission and UV emission from the sun. We document that exactly in this time there was a significant solar flare. Not the largest, it was this 10.3. So not solar flare, but nevertheless it was very nicely detected by us. And here one can see for 20 minutes of data, and one can see that when solar flares appears, here is UV and here is X-rays, one can see significant increase of measurements of azimuth measurements. And it is because the attenuation of ELF waves decreased significantly. And it can be seen a little bit if we look into our signals before the flare and during the flare. I claim that there are much more spikes visible. They are not attenuated, they are stronger when they come. Also, if one can see for this global lighting monitoring system, one do not see any increase of lighting during this Yeah, so it means that it's not the larger number of language, but simply lower attenuation of words. And it can be also seen in such plot, maybe not very clear, but on the frequency here up to 650 Hz. And here is time from 10 minutes past 2 up to 2:30, and the flare maximum of the flare was at 18 minutes past 2, and one can see that significant some difference plot between average and current measurements. And one can see that the spectra are much higher starting here. So it means the absorption is much lower. And maybe in the end, let me show us a very interesting study which we can do with this system, which is monitoring big lightnings all over the world. And it is a frequency range here, so it shows exactly where is the lightning occurs. And during this day, with the flare, we simply study how lightning occurring in Africa and in America are registered by our system in Krakow. And so we consider only lightning between 5 and 9,000 kilometers from us. And the procedure was more or less like this. At first, we derived when the lightning should reach the station, and then we look for nearest input to this expected time, and we consider that we provided the proper time for a given line. And very interesting deviation we have seen. So here are our measurements of this time delays. From this time delays, we have velocity of propagation of this signal. And one can see that during the night, when there is this lower layer of ionosphere, propagation is relatively fast. It's 0.95 of light velocity. From 1 up to 0.75. But when there is sunrise, then it's particularly interesting structure of this. During the day, propagation is maybe much slower. Around 0.85 of velocity of light. These such special structures during this sunrise and sunset times. And it is from Africa, from America, when impulses are going closest to the pole, ionosphere is significantly different. One can see the same plots when you derive for South in America. And one can see it is for 2 successive days, and one can see that the shape of structure is quite similar, but there are different. And on both days there was a solar flare of this M-type, so one can see the structures of the solar flare in different times, of course, visible on both these. And this flare, if we compare this flare with UV flux from the sun and X-ray flux, we can see that at least here X-ray flux seems to be better better fit the shape of the changes of the velocity of people propagation. So, so it is thank you, sorry for today, and sorry for being too fast and trying to answer all the questions.
Thank you very much. Thank you, Michał, for a great talk. Do we have any questions, comments? Anyone? Sarek?
Okay, so suppose you can figure the vector on the surface of the moon. What kind of astronomical sources would you look at?
So essentially, to my knowledge, of the moon is the atmosphere is so thin that possibly there is negligible ionosphere of the moon. So I believe that no measurements could be possible. But very interesting proposal was considered 2 years ago, namely to use such detectors on Mars. On Mars, atmosphere is much more, and we know that there is ionosphere. And also the structure of the ground on the Mars is maybe quite dry. Because water is important for us to allow currents and to use this resonance time. So in the case of Mars, if we put such detector on Mars, then possibly we could measure how much water is there is water underground in Mars. There were some models saying that maybe significant fraction of the Mars is dry, but it could be checked.
And I was actually wondering, because recently we could see auroras in Gestade. Could you somehow detect it in your data, or it's completely different frequency?
Essentially, it is one of topics which we have to study in more detail. So of course, when there were these auroras, we took our data, we looked into this value distributions, power spectra, and there were some additional noises, but such noises were also generated sometimes due to other reasons. So it required more careful study. But in principle, we expect that changes should be observed. In particular, for impulses propagated close to the poles, then they should go to the part of the ionosphere disturbed by this energetic part.
Do you know how many indicator you use?
I think that there's of course so-called Cracow detector, which we try also to learn forever in this house. And to my knowledge, maybe there were some expectations for military use of HARP 30 or 40 years ago, but there is no such option now. It's purely scientific program. And such measurements are of course of significant importance for military because we are studying ionosphere. And ionosphere is an important factor for GPS system. So the additional measurements of ionosphere would help control the GPS system, but I don't. It is just quite general comment because I don't know any detail about how to apply it. We know about this low frequency signals which are Russian sending to their submarines. In US, people used to send such signals at 75 hertz, and we could measure it in the beginning of our measurement, but later the measurement decided to skip such type of communication. And in Russians, there are still such signals observed in our data. But I understand there is a emitter which is in Cola Peninsula. There are some Norwegian amateurs who are measuring these emitters from nearby short distances and also analyzing. So I don't think we could do something particularly interesting.
I can see, yeah. Like,
Okay, yeah, so my question is, can you determine thunderbolts and by this mechanism?
So that thunderbolt is sound. Yes. So do you use that?
It's like lightning, which is.
I'm not sure if I understand what I understand.
the one that can produce
But-
microwave this thing, right?
But essentially, these measurements can be done if the lighting is very small. If the lighting is, and then we observe low frequencies, and we can measure, for example, we can measure so-called charge moment. So how much charges are moved in the light. In the case we are close and our equipment is fully the signal is too strong to be analyzed here, and also the waves may not simple way of propagating using the resonance. So in principle, we can measure how strong was thunder. I call it lightning discharge. And also sometimes it's lightning discharge which are not like one side, but there is discharge of the current which is following the discharge. So this type of changes are observed in the impulses.
I think our time is running out, so if someone else has a question, could come to Michał after the talk. Thank you very much once again. There's no announcement. There is no seminar next week because we are involved in two conferences that are going on in Warsaw. So we see each other here in 2 weeks, and there's going to be a talk about Gaia Black Hole 3 given by Pascale Panuso. Thank you very much.
Okay.
Thank you. Bardzo dziękuję.